So good morning everyone. Today we'll start with the next topic, infinite impulse response filters. In short we call it IIR filters. Okay. So till our last class we have been discussing about the FIR filters. So what was the basic phenomena behind the FIR filters? FIR stands for finite impulse response, and we have already discussed that if we are given a system which is having an impulse response of Hn, so if we give delta n as the input, we will get this Hn as the output. However, if we give some input to the system, then we will get Yn, which is equal to x of n convolution of h of n. So, this thing. Now, this impulse response, in the case of the FIR filter, we saw that it was finite in nature. However, in the case of IIR filters, what happens is that on the contrary to the FIR filters, in IIR filters this impulse response would be infinite. Okay, but what is the condition over here? So we may have an infinite number of this impulse response values, but at time t tending to infinity we should have the Hn values which should be tending to 0. Okay, so at time tending to infinity we should have Hn tending to 0. It cannot be 0 because we are it cannot be 0 because we are saying infinite impulse response filter, that means it would be having some values. Okay, but those values should be tending to 0 if you want to design a stable filter, stable IIR filter. Okay, say for example, if we have a system whose Hn values it remains constant, it is growing not out of bound, not it is decaying to 0. So such kind of system, so this is n and this is Hn. Okay, so what happens over here? It is not growing out of bound also, it is not unstable, and also it is not coming down to 0. So you cannot say it is a stable filter. So such kind of filters, they are regarded as neither stable nor unstable filter. Okay, neither stable nor unstable filter. In other words, you can say marginally stable filters. And how this condition appears is that we have discussed the pole 0 plot. Previously, so this is the Z plane. This is the Z plane. Okay, so this is the real Z and y axis is the imaginary Z. Okay, so over here what we have is that we have a pole on the unit circle. We have a pole on the unit circle, and when this happens, this kind of situation it arises, that the these HN values, they are neither going out of bound nor it is coming down to 0. Okay, so this is, I have just given you one example. So why that is so? This is because if you look at the position where this pole has been placed, in all other positions you will be getting a definite distance values, right, to the frequency, to that frequency component. So you are having some distance values, and because of that you will be getting some gain. However, at the position where you have put the pole, what is happening? The distance becomes 0. So what will be the gain? The gain will be the infinite. So the system that you have designed, it is unstable only at that particular frequency. Okay, only at that particular frequency, and because of that we can see this kind of response where the impulse responses, they are remaining stable. This we did not get when we were discussing FIR filters. Why? While we were discussing the FIR filters, one of the major advantage was all the filters were in all the poles, they were inherently present at the origin of the Z plane. Okay, and due to that the FIR filters were inherently stable in nature. But when we are talking about the IR filters, in the IR filters poles can be placed anywhere as per our liking. So here comes the problem. You say when you have a particular higher position, it comes with the responsibilities. So when you are talking about placing your poles at any of the locations, so basically what we are doing, we are increasing our responsibility, and when we are increasing our responsibility, we have to be very careful so that all the poles, they lie within the unit circle. Okay, if it is placed onto the unit circle, then there is a problem. If it is placed outside the unit circle, then also there will be a problem. The system will become unstable. If it is on the unit circle, then it would be marginally stable, and if it is placed outside the unit circle, it will be totally unstable system. Okay. Now, in the first case, if you see, we are given with this hz equals to 1 plus b z inverse plus c z to the power minus 2 plus d z to the power minus 3. So this is the equation for the transfer function for the FIR filter. Okay. Now, if we want to find out the pole and zero locations, what we did is that whatever is the highest power of the Z inverse, that we multiply in both denominator and numerator. Okay. So by doing so, we get such kind of equation, and when we get such kind of equation, we get two polynomials, and if we solve the polynomials, numerator, the roots of the numerators, it will give us the position of the zeros, and if we equate the denominator, then we will get the positions of the poles. Okay. Now, in the case of IR filters, what happens? If you look the transfer function, it would look something like this. Okay, so we have taken a very simple transfer function over here, 1 plus b z inverse divided by 1 plus a z inverse plus z to the power minus 2. Okay, so what would be the order of the filter? So order of the filter is 2, hence we have to multiply both the numerator and the denominator with z square values. Okay, now in the numerator I have taken 1 plus b z inverse. You could have taken 1 plus b z inverse plus c z to the power minus 2, doesn't affect what I want to say. Okay, so in that case what will happen? Again the order would have been the same. Okay, because we will be looking into the highest order of the z inverse both in numerator and denominator. Okay, and we know that the number of poles should be greater than equal to the number of the zeros. That means if we check the denominator for a stable filter, if we check the denominator from the order of that one, we will be able to tell whether what is the order of that filter, right? Now this hz, it is equal to yz divided by x of z, right? Now if you try to solve it, yz plus a z inverse yz plus z to the power minus 2 yz equals to xz plus b z inverse xz. So if we solve for yz, we get this equation. Now what does this equation tell us? What does this equation tell us? This equation tells us that the current output, it is dependent on the present and past inputs. Apart from that, it is also dependent on the past outputs. So that means what happens is that in FIR filter, this was not the case. In FIR filter, if you check over here, if you put hz equals to yz by xz, so yz would be equal to multiplied by this equation, because denominator over here is 1. So we would have directly got the output. So in the FIR filter, what was happening? The output was dependent on the present and the past inputs only. However, in IR filters, the output is dependent not only on the present and the past inputs, but also on the past outputs. Okay. Now then, if we go and try to realize the filter, we have this equation yz equals to this one, and we take it and try to realize the filter, we will be getting this realization. Now if you see, for calculating yz, we are basically taking the inputs, and these delays, they are making the utilization of the past outputs. Okay, so the past outputs are being taken to calculate the present output. Okay, so this is called the feedback mechanism. You are getting a feedback from the output of the systems, right? Now if you take the inverse Z transform, you will get this one. Okay, yn equals to xn plus b x of n minus 1 minus a of y of n minus 1 minus of y of n minus 2. Okay, so this is the difference equation. Now let us take a simple example. Hz equals to 1 by 1 minus a z inverse. Okay, let us find the location of the poles. So highest power is z1, so it would be z to the power 1 multiplied in both numerator and denominator. We get z in the numerator we get z divided by z minus a. So in numerator z equals to 0 and in the denominator we get z equals to a, right? So we have a condition where z equals to 0, z equals to a. 0 is placed as 0 means at the origin 0 has been placed, and a we can modulate. Now let us take three cases. A equals to 0.5, a equals to 1 and a equals to 1.5. Okay. Now we have to realize the filter. For realization, if you see, hz equals to yz divided by xz equals to 1 by 1 minus a z inverse, which equals to yz minus of a of z inverse yz equals to x of z. Okay. So yz equals to x of z plus a z inverse yz. So we get xz, then we have an adder. This adder is again, then we are getting this yz formula, so we will directly take the yz, but over here we have a delay function, one delay is there, so delay is being added, then a is the multiplier over here, then it is getting added, right? So in the simplest term, what you can say, xz goes to the adder, then you take the output, so this is the thing, but we have a second component also, z inverse multiplier goes to the adder. It is as simple as that. Then let us take 0.5, 1 and 1.5. So when it is 0.5, when we give xz, we get xz, we are giving the input impulse. So we want to find out what are the impulse response values. So we give impulse response xz equals to 1 0 0 0 would be there. Yz, we can find it out. This would be the yz, right? Then when a equals to 1, when a equals to 1, xz equals to again 1 0 0 0. So you have this 1 at time instance equal to 0 and then again 0 0 input. So for that, you see the output is 1 1 1 1 1. It is going on. Okay. In the third case, if you see, for the same impulse input, the values are continuously growing. So at time tending to infinity, there would be an unprecedented increase in the amplitude values. Okay. So from this three case, what we see, when the pole was within the unit circle, the values, Hn values, they were coming down. When the pole was placed onto the unit circle, we got a flat amplitude Hn values. Okay. And when it was outside the pole was outside this unit circle, then the Hn values, they were growing out of bound. Okay. So with this, from the next class onwards, we will be starting with IR filter design. So first one is the impulse invariant method, second is the bilinear transform method, third is the frequency transform method, and last is the approximation of the derivatives methods. So these four methods we will be discussing from the next class onwards. So I am not going into the details at this moment, because we have certain examples which you need to understand. Okay. So we'll stop over here. So what I would ask is that I have given you this signal flow graph diagram. Now you calculate this Hn values, because as we go for the next numericals, so the system will become more complex. So you get your hands on with these 3 examples. You find out how this is happening, how these values are coming. Okay. So we'll stop today here.